Hi. Hi, Isabel.
Okay. Wow, this is cool.
Yeah, so we are live. So I'm just going to leave the flyer up and then this is being recorded, but hopefully I can edit the video later.
Hi, everyone. Thanks for joining us for West LA's first ever Astronomy on Tap, where we bring knowledge of the cosmos to a local and currently virtual bar here in Los Angeles. Tonight's show features two members of the astronomy department at UCLA, sharing their cutting-edge research on the nature of our universe. We'll also be taking questions through the YouTube chat, so feel free to post questions if you have any for our speakers in there. For a brief introduction, my name's Isabel. I'm a grad student at UCLA, and I'll be introducing our speakers tonight. We'll also get some help from my colleagues, Isabella and Kelly, who will be monitoring comments and questions in the chat and leading trivia. First up, we have Anna Chirlo. Anna's a postdoc and Keck visiting scholar at UCLA. She earned her physics degree in Genoa, Italy, and her PhD in astrophysics at the Observatory of Paris, France. She's interested in the complex environment at the center of our galaxy, especially its effects on the gas clouds and clumps, which she studies through a technique called imaging spectroscopy, which you'll learn more about. She's also a member of the Galactic Center Group, a name that might sound familiar to some of you because of the recent Nobel Prize awarded for Andrea Ghez and her work in this group on the discovery of the black hole at the center of our galaxy. Anna is here today to tell us more about this, so let's hear from her. Take it away, Anna.
All right, thanks, Isabel. Hi, everyone. I'm very happy to be virtually here. Thank you for having me. Too bad we are not all together in a nice bar, but maybe next time. So yeah, today I just want to give you a brief overview of the interesting and fun things we can learn about looking at the center of our galaxy. So let's start with the first question. What is our galaxy before we start talking about its center? So basically what happens is that stars and planets and so on don't just live alone in the universe. They live in what we can think about as cities of stars, and that's what we call galaxies. You can actually see our own galaxy, the Milky Way, if you look at the night sky in good conditions. So in LA, that's basically impossible. But if you go in the mountains or in the middle of the sea and so on, you might have seen this already. It looks like a trail of clouds that crosses the whole sky. What you see when you look at this, it's the visible part of our own galaxy, the Milky Way. So the name comes from the fact that it looks like a stream of milk that is across the sky. So the white light that you see when you look at the Milky Way, it's made of the combined light of hundreds of billions of stars. But then in between these stars and ourselves, there are a lot of clouds that stop some of the light, and that's why it looks like clouds. So again, the name just comes from the white color that you see when you look at it. So the shape of our galaxy is actually the shape of the disk. However, since we are right inside of it, we see it in the sky as a band. So we cannot travel outside of our own galaxy because it's way too far, but we can use galaxies around us to have a pretty good idea of what it would look like to see our galaxy from the outside. So this galaxy, for example, show us the Milky Way, we see it in the night sky, so a band of clouds and light. Now we can look at other galaxies that can give you an idea of what it would be when you look at it from above with the bird eye view. So that's what it looks like. So as you can see, this is a disk, and it also has some beautiful spiral arms. It's a very nice object, and we with the solar system are right inside of it. So when we look at it in the night sky, we just look through its disk because we are right inside of it. So our galaxy, as I've been telling you, looks like a disk. So you can think about it as a very big pancake or a huge pizza. I'm originally from Italy, so I very much like this idea of a gigantic pizza that is actually our galaxy. And let me try to tell you how big. If you think about the salt on the pizza, basically you will be able to fit the whole solar system, all of it, inside just one grain of salt hundreds of times. That's how big it is. So the whole galaxy has a diameter of about 100,000 light years. As a reminder, 1 light year is 6,000 billion miles. So imagine this 100,000 times. It's a very big distance. The solar system and the Earth are located at around 26,000 light years away, which means that when you look at the Milky Way in the sky, the light that you see started from the very center 26,000 years ago when we were still in caves making drawings. And it traveled all the time until you can see it today. So think about that next time you look at the Milky Way. So But when we look at the Milky Way, we see a whole band in the sky. But where is exactly the center? Well, you can find it yourself. If you can spot the constellation of the Sagittarius, traced here, that looks more or less like a teapot that is pointing you toward the galactic center. So now, for example, in this picture, the galactic center is here. Now, this picture is very nice. However, as you can see, and the point that the arrows is pointing at, we don't see much because there is so much of these clouds that are stopping our view. So what we need to do is look at different wavelengths. So basically, when we look at the world around us, we are only looking at the given number of colors, but these are not all the colors that exist. We can build instruments that allow us to look into the radio, the infrared, or the X-ray light, for example. So this is very powerful because depending on which light or which wavelength you're looking at, you can see different things. And for example, if you look into the visible, this is a very beautiful nebula. It's very nice. You see all these clouds, but all these clouds basically stop the view of what is behind them. If you look in the infrared, you can look through the clouds and have a completely different view. Or again, if you look in the X-rays, it's exactly the same area, but you see something very different. So let's apply this to the center of our galaxy. This is the visible, it's very pretty, but we cannot see very much. Now let's switch to the infrared light. That's what we see now. It's exactly the same image in the same scale, but now looked at in the infrared. Now you see that this time it's very easy to find. The center of the galaxy is right where the brightest spot is, and we can see so many more stars. It's very nice. So it seems like there is something interesting in the center of the galaxy. So let's try to zoom in and approach the center. So here we see some complex structures of gas. We have this ring that is orbiting around the center. We have these arms of gas that are stretched and are infalling toward the center. So, but this is just the gas. Let's look at the stars at the same scale. There are a lot of stars. Let me just try to explain you how many stars. So if you think about the Earth, we are orbiting around the sun. The sun is our star. The closest star to the sun is Proxima Centauri, that is 4 light years away, more or less. So if you trace a circle here, in this area, there is only one star, the sun. Now, in the exact same area, in the center of our galaxy, there are 10 million stars. So it's a very extreme and very crowded region. It's very far. You have to look in different light than the light we can see with our eyes. So how can we study this very complex and interesting region? Well, we need to use very powerful telescopes. One very good telescope to do that is the Keck Observatory on the Big Island of Hawaii. So this is a very big telescope, one of the biggest currently existing in the world. It's 2 twin telescopes. Each one of them has a mirror inside that is 8 meters diameter. So to give you an idea, this will be my size compared to the size of the telescope. I'm not very tall, but still, it's pretty big. So this not only is a very big telescope, but it's also equipped with a great technology that is called adaptive optics. Basically, what happens is that you can build very big telescopes on Earth, but then you have to observe the sky through the atmosphere. And the problem is that the atmosphere basically blurs out your images because of turbulence in the atmosphere. So the way we can deal with it is using adaptive optics. What you can do, basically, you shoot a laser through the sky that makes a fake star that you can observe. And you can basically correct in real time the turbulence of the atmosphere using this fake star. So this video is supposed to show you a little bit how this works. So the turbulence of the atmosphere perturbs your image. So this chips looks like the perturbed atmosphere that comes to a computer when you just observe through the atmosphere. Now you can use its information coming from your laser to actually feed it back to a mirror that is deformable and that in real time can basically correct for this deformation, making chips that are now very flat. So now, for example, when you don't use adaptive optics, this is the image of a star. It's twinkling a lot. When you switch on adaptive optics, it becomes way more focused. Let me show you what it looks like in the galactic center. So on the left, you have the lasers used by Keck. This is not a fake image. We are not painting on the image. This is really the lasers as you can observe them in the sky. And so on the right is an image of the galactic center taken without adaptive optics. Now, if we switch it on, what happens is that you start to focusing very much and you can see way more stars this way. Okay, So how do you do that? Well, you have to apply to observe with this great instrument, the SCAC. If you are lucky and you get the time, well, the 2 telescopes are on the top of Mauna Kea in Hawaii. Usually just go to the headquarters and observe during the night. It's very tiring, but it's also a lot of fun. Unfortunately, now due to the pandemic, I have been doing it alone in my office, but hopefully we will go back to the headquarters soon when this is over. Okay, so with this type of instrument, we can take different type of data. We can take images, that's pretty straightforward, pictures basically in the infrared, in whatever wavelength we want, or we can take what is called imaging spectroscopy. So basically you can take your image, not just at one color, one wavelength, but at multiple wavelengths, which give you access to the spectroscopic information of your source. So now why is this interesting? Well, spectroscopy is actually very powerful. What is it about? Well, if you think about a star emits light. If you pass the light of the star through a prism, for example, as it's shown very nicely, very famous band album cover, what you obtain is basically a rainbow. This is exactly the same process that create rainbows. What happens is that raindrops in the air separate the light that comes from the sun and separate in different colors. So this is just the basic. It's what we call a continuum. Now, if you have a cloud, for example, in between a star that is emitting light and yourself, the prism, what you have is that in your spectrum, there are some absorption lines because some of the light has been absorbed by the cloud. On the other hand, if you have a heated cloud that passes through your prism, you can have emission lines coming from it. So this alternation of absorption and emission over a continuum is what we call a spectrum. So let me show you here a real spectrum taken of the galactic center. So you have this baseline and you have emission and absorption line on top of a lot of noise, of course. Now, if you look at the absorption lines, this can help you actually identify stars that are in the galactic center. On the other hand, if you look at the emission lines, you can look at the emission from gas clouds. So let's start with the stars. Here is the picture I showed you before. Now we're going to use SCAC to observe this very tiny region. First of all, let me just dim the light a little bit. So now I'm going to focus only on this tiny region. So this is a zoom in. What you see here are a lot of different stars. And what I'm going to play for you is an animation that shows you a picture taken of the stars year by year for 25 years. Let's look at it. So first of all, you can notice that everything is moving. Every single thing is moving in this picture. But if you look, for example, at the star that is in the very center, you can see that we traced a little bit of a line because it's basically making a whole orbit around one single point. And if you do the same for all the other stars in this region, you can create something that would look like this animation. So this is a very nice animation that basically shows you what you would see if you could fly by the galactic center and look at the stars as they orbit around the very center. Of course, we cannot do that because we are way too far away and the stars don't orbit quick enough for us to actually see them this way, but it's a nice animation to just give you an idea of what it would look like. Okay. So the thing is that everything is orbiting around something, but now what is that something? Well, before we address that, we need to talk for a moment about gravity. So gravity is what allows us to stick on Earth. It's also what makes the moon orbit the Earth, what makes the Earth orbit the sun, and also, of course, what makes the solar system orbit the center of our galaxy. So basically, when you look and study something that orbits something else, you have information of the thing that is in the middle that is making it orbit. So now, looking at all those stars that I showed you before orbiting around the very center, we were able to measure that actually. In the very center, there is a mass that corresponds to 4 million times the mass of our own sun, concentrated in a volume that is basically the same volume that there is between the sun and one of these planets. So this is, imagine just putting 4 million sun inside our own solar system. This basically makes an object that is extremely dense, and an object with this density can only be a supermassive black hole. So this is not just a black hole, it's supermassive black hole because of its great mass. We said 4 million times the mass of the sun. So this nice image was taken from one of the papers that came out when Interstellar came out. So this is just a simulation of what it would look like to look at a supermassive black hole. So this is a very extreme object right at the edge of our knowledge. And basically the gravity around this object is so strong that it bends the space around it so much that light is trapped inside it cannot come away. The light that you see here is basically coming from material that is either orbiting the black hole or is behind it and has not fallen yet inside the black hole itself. So let's see, just looking at the stars and their motion, even though it's complex from the technology point of view, gives you a very simple and direct proof of the existence of supermassive black hole. And this is exactly the way that we used 20 years ago to demonstrate for the first time the existence of such objects. And that's what was recognized this year with a Nobel Prize in Physics to Andrea Ghez and to other researchers. So we cannot observe black holes directly because they trap the light, so they don't emit any light, but we can see the material as it falls into the black hole. And for example, about a year and a half ago, we observed again the supermassive black hole eating a little bit of material. So if you look at the very center of this image, I'm going to play an animation and you're going to see a change in the image. So see, it's super bright at the beginning and then it gets dimmer. The moment when it's super bright, it's the moment when we believe a little bit of gas was fed into the supermassive black hole. So you just saw a black hole having its dinner, basically. Okay, so all this was just, but not only stars orbit the supermassive black hole. Let's now focus for a moment on the gas here. So I showed you before the nice animation showing the motion of the stars. Now we're gonna just look at the gas. So these three blobs that are identified by the red circle are blobs of gas, and let's see how they evolve with time. So as you can see, it's not as nice as the other animation, but still it's pretty clear that these objects are moving. So what we can do in this exact same way we did for the stars, we can trace orbits for these objects. So these objects, since they look like gas, were named G objects, but their orbits very close to both the orbits of the stars. So what are these things? We don't believe they are just made of gas, because otherwise they will not just keep orbiting the black hole, but at some point they will just fall into the black hole and be eaten in the same way I showed you before with that tiny animation. So we actually believe that these are stars in disguise. And basically, we believe there is a star inside that we don't see because it's basically hidden inside a layer of gas and dust. What you see here is just a nice artistic impression of what these objects might look like. In the very center, there is a star, then there is dust around that is represented here by the red color. And then around it, there is a shell of gas that is ionized by all the stars that are around it. The black dot in the very middle is a massive black hole. Now, the question is, why do these stars look the way they do? Why don't they look like normal stars? Why don't we only see the gas emission from it and not the star? We have to find a mechanism that basically explains why we have all this material around a regular star. So there are many hypotheses to explain this phenomenon. One of those that we like the best is that these are the produce of binary mergers. So what happens is that very often when stars are formed, they are not formed as one single star, but they are formed in a pair. This pair is what we call the binary. So if you have a pair of binaries, sorry, a pair of stars, so a binary, into the galactic center, you have two stars that basically orbit each other and together orbit the supermassive black hole at the center of our galaxy. Here, this is marked by the text Sagittarius star because that's just the name of the supermassive black hole at the center of our galaxy. So we were saying you have these two stars orbiting each other and orbiting the supermassive black hole. Now, what happens is that because of the presence of the black hole, these two stars can get close enough to each other that they can start stripping material one from the other. So they keep doing this as they orbit the black hole, and then this happens more and more until you actually completely destroy the two objects and you have just one object. You merge the binary. The thing is that when you do this process, it takes some time. You are going to shed a lot of material because it's a very messy process. So this very nicely fit with what we see for the G object. We see an object that stays compact, that orbit the black hole, but only show emission in gas. And this gas most likely was created by the merger of these two stars. So all these things we're able to do them with the Keck telescope. A lot of these studies have also been carried out through the Very Large Telescope, the VLT. These two are two of the biggest telescopes existing today on Earth. However, there are many plans to build even bigger telescopes. So here you have to scale. The Keck VLT, a basketball field, just to give you an idea of the sizes, and then the size of the 30-meter telescopes, or TMT, that is in construction now in Hawaii. And here you also have the extremely large telescope that will be even bigger. And just to give you again an idea, my size next to those will be super tiny. So imagine all the things we will be able to do with these even larger telescopes. It's pretty amazing. So here on the right, I just put the size on scale of the Hubble Space Telescope and the James Webb telescopes. The HST Hubble Space Telescope is on the sky now, whereas the James Webb telescope will be hopefully sent into space next year. And as you can tell, they are way smaller than even the current telescopes that we have on Earth. This is just to show you how hard it is to actually send telescopes in space. It's very expensive and you cannot make them as big as you want, whereas on Earth, you pretty much can. I want to give you a very brief idea of what we can do with these telescopes of the future. So on the left, you will have an animation of the motion of the stars in the center of the galaxy using Keck at its best. So the best we can do looking at the stars with Keck. On the right is what we will be able to do with the 30-meter telescope when it's built. So let's play it. So as you can see, with TMT, you see so many more stars. You can detect way fainter stars. You can follow them very well. So we will be able to study this region even better. So basically, this is just a few examples of the many interesting things we can learn from our own galaxy, and specifically from its very center. It's very exciting, it's very interesting, and we can observe it with very powerful instruments, and it's also a lot of fun. And of course, when you look at the Milky Way next time at night, just think about all the things that are going on inside its very center, and also enjoy the beautiful view of our very nice galaxy. And I think that's all for me. So thank you very much for the attention. Okay, so I guess we can take some questions now. I guess I'm supposed to read them. Okay, so I'm going to read to every one of you the questions that I see. Just before I start this, cheers everybody, we're supposed to be in a bar, so. Okay, first question, in the video of the black hole swallowing some gas, why did the image get brighter when the gas was swallowed? That's a good question. So we believe that basically what happens is that in general, you have the black hole and you have a lot of material that orbits around it. So this material is basically far enough not to be eaten by the black hole immediately, but is just orbiting around it. So what happens is that sometimes when some of this gas gets inside, it gets accelerated and it's passing through the rest of the material very quickly in a very energetic way. And so basically it's just enhanced around the black hole itself. So it's not that we are actually seeing the black hole itself, we just see what happens to the material just before it gets swallowed by the black hole. I hope that answered your question. Second question, do all other galaxies have center that looks like ours or they differ? This is a very good question. So we believe that most of the galaxies that look like ours, so that look like this with spiral arms and so on, have a supermassive black hole at their center. So the idea is that we're going to look at the center of our own galaxy because it's the closest to us. The closest galaxy to us is 100 times further away than the center of the galaxy than the center of our own galaxy. So we can observe our galactic center at way much higher resolution. And now the question is, how much can you generalize your results to other galaxies? And this is a good question. And we hope we can pretty much generalize it. There are many different types of galaxies. So there are more or less active galaxies. For example, I showed you the animation of the black hole eating some material and getting slightly brighter. This is nothing compared to what some other galaxies can do. Sometimes the black hole is so active that the whole center is way brighter than the rest of the galaxy. This is what we call active galactic nuclei. And so some of these galaxies look very different, but still the processes at play, a black hole, the stars around, the black hole feeding and so on should be close. So we can probably generalize some of the things and understand, even though not every single galaxy looks exactly the same, but maybe also because they're not exactly at the same stage of evolution and of what actually is going on. But we can say that our galaxy is pretty standard. So hopefully that can help us understand most of the other galaxies. Okay, are there any other questions? I guess not. So cheers again to everybody, and hope you enjoy the next talk. Thank you for having me again. Bye.
Thanks so much, Anna, for such an incredible talk. So we're going to shift gears now a bit and come a little bit more close to home and hear from Judah Van Zandt. Judah is an astrophysics PhD student at UCLA, and he's also a member of the California Planet Search team, where he studies planet detection and characterization techniques. His current work focuses on the broad demographics of these planets and how they put our solar system into a bigger context. Take it away, Judah.
Great, thanks, Isabel. All right. Hopefully everybody can see my screen now. Yeah, fantastic. So, one second. Good, yes. So, like Isabel said, my work focuses on the detection and characterization of exoplanets, and specifically right now, I am working on a demographic study that we're calling the Distant Giants Survey. So at its heart, the Distant Giants Survey is a statistical study of exoplanet demographics. So in order to contextualize this work a little bit, I'd like to first give some background on what exoplanets actually are. So an exoplanet, or an extrasolar planet, is any planet that orbits a star other than our own sun. So exoplanets have been kind of the subject of popular science and of actual science for a long time, but it's only relatively recently that we have obtained concrete evidence for their existence. So the first exoplanet that was discovered around a sun-like star was discovered in 1995. It's called 51 Pegasi b, and it was recently honored with the Nobel Prize in Physics in 2019. So astronomy has actually enjoyed quite a bit of attention in the last couple of years. And since then, there have been more than 4,000 new exoplanets that have been detected. And so this has basically allowed the exoplanet field to grow by leaps and bounds in a very short time scale. It's a very rapidly growing field. And in that time, exoplanet researchers have developed a very robust arsenal of exoplanet detection techniques. And I'd like to talk a little bit about two of them that feature very prominently in my work. So the first and one of the most well-known exoplanet detection techniques is called the transit method. It is well known as the most prolific, or you could say the most effective exoplanet detection technique, because it has been responsible for over 3,000 of the 4,000 exoplanet detections to date. So the mechanism behind the transit method is actually relatively straightforward. Exoplanets, by and large, are too dim for us to see, even with very powerful modern telescopes, but their host stars are extremely bright. And what's more, we can measure the brightness of those stars and fluctuations in that brightness with extremely high precision. And so that means that although we can't see these planets, we can measure fluctuations in their star's brightness to search for clues as to their existence. And specifically what the transit method leverages is the fact that a lot of exoplanets actually pass in front of their host star with respect to our line of sight. That is to say that when we look out at a star, a lot of them have planets that during the course of their orbit pass between us and the star. And this results in a periodic dimming effect in the host star. So you can see in the graphic at the right, we are observing the brightness of this star, and we can quantify it. And then every now and then, although we can't see a planet, the brightness dims for a period and then recovers its original value. And so we can interpret this as the planet passing in front of its host star. So some benefits of this technique, first and foremost, are that it's proven to be extremely effective. Transits are responsible for over 75% of all exoplanets. It's also useful for detecting a particular type of planet, namely planets that are close into their host star. They have a short or a small orbital separation is also another term for this, because planets that are close into their host star have a higher likelihood of transiting. And as they move out farther away from their host star, there's a smaller range of angles that planet could occupy while still transiting. So broadly speaking, planets that are close to their host star are more likely to transit. This technique also has some drawbacks, however, going along with what I just said about about the transit method being effective at detecting close planets. It's not as good at detecting planets that are far away because it requires basically an edge on orbit or something close to it. So planets that are far away will often orbit with will often have a slightly inclined orbit, or declined, so to speak, which basically means that as they pass in front of their star, they kind of go over or under our line of sight. And so they never dim their star from our point of view, and we're not able to detect them. Another drawback is that one of the key parameters in exoplanet analysis that helps us to determine the composition of a planet and its formation history is a planet's mass. But the transit method doesn't really tell us anything about a planet's mass. It can give us really good constraints on a planet's radius and therefore its overall size, but we don't really know how massive a planet is, and therefore we don't really know its composition based purely on the transit method. So this is where another important and complementary method comes into play. So the radial velocity technique is another way of detecting and characterizing exoplanets. I like to think of it as being complementary to the transit method in the sense that it can fill in a lot of the gaps that the transit method leaves kind of unanswered. So the basic method behind the radial velocity technique is that planets orbit their host star, but at the same time, those stars in some sense orbit their planet as well. And more accurately, both the star and the planet are orbiting the system's mutual center of mass, which is depicted as a blue cross in the diagram at the lower right. So again, we can't see most of these exoplanets because they're too dim, but we can see the star. And as it moves back and forth in the sky, we can detect this kind of stellar wobble, as it's often called, as shifts in the frequency of the light that we receive from the star. So normally, a star will emit light at virtually all wavelengths. We get blue, green, red, ultraviolet, and infrared light. And in that stellar spectrum, there are little kind of mile markers, or like little indicators to kind of orient us. So a certain spectral feature might exist at a particular wavelength. When the star is moving toward us, all of those wavelengths are blue shifted, which means that all of the wavelengths that should have existed at a particular value, if the star were stationary, are shifted more toward the blue end of the spectrum, towards shorter wavelengths. And so by watching where these spectral features move, we can determine that the star is actually moving. And likewise, when the star moves away from us, those wavelengths are red shifted. So this is known as the Doppler effect, and it occurs with all wave-like phenomena and a more intuitive version of this would probably be for sound, but it actually occurs with light as well. So examples of how this effect works they can be found in our own solar system. For example, the Earth causes a radial velocity on the order of 10 centimeters per second in the sun, which means that because of the Earth's orbit, the sun rocks back and forth at a maximum rate of 10 centimeters per second. We can compare this with Jupiter, a much larger planet that is farther away from its star or from the sun, and it induces a radial velocity of about 10 meters per second, or about 100 times as large. So broadly speaking, larger planets are easier to detect than smaller planets because they cause bigger shifts in their stellar spectrum. So some benefits of the radial velocity technique are that it does, unlike the transit method, give information about the planet's mass. It also gives information, or let me actually back up, it gives information about the planet's mass in the form of a radial velocity semi-amplitude, which I already mentioned for the Earth is about 10 centimeter per second, for Jupiter is about 10 meters per second, and in a more quantitative sense, this semi-amplitude is represented by the maximum height of that curve that is in the diagram at the right. So more massive planets will achieve a greater height in that curve and a greater depth, actually, than smaller planets. And small planets will kind of oscillate around zero, but will have a smaller amplitude. So the star doesn't move as much for a smaller planet. Another benefit is that radial velocities are sensitive to non-transiting planets, which fills in the gap that transiting planets kind of miss. So even if a planet transits over our line of sight or under our line of sight, it will still induce a radial velocity that we can detect. It does have its own drawbacks, however. For example, the radial velocity technique is limited by stellar noise. And so this means that basically the internal processes that are taking place within a star kind of mimic or cloud radial velocity signals on the order of about 1 meter per second. So you can imagine this kind of like static in a television. If you're trying to observe a very small signal, but there's a lot of static clouding it out, then you're not going to be able to see anything below a certain level. And for a lot of stars, that level is about 1 meter per second. And so Earth-like planets are more or less unachievable for current technology. Whereas Jupiter's are well above the threshold for detectability. And then another drawback is that we only are able to determine the mass to within a certain factor, because if those planets do transit not in an edge-on orbit, then we don't know exactly how much of that tug on the star is in our direction versus at some kind of diagonal direction. So there are some questions that are left unanswered by the RV technique, but overall, both of these methods together give us really strong information and a really robust picture of a planetary system that we can use to do extremely useful science. Okay, so here I have a diagram of most of the exoplanets that have been discovered to date, and I'd like to draw your attention in particular to the lower left, which represents a particular demographic of planets known as close-in subgiants or close-in subjovians. These are stars which are relatively close in to their host star and relatively light. They're not very massive. So as you might expect, most of these stars were detected using the transit technique because they're more likely to transit being close into their star, and they don't have as strong of an RV signature. On the other hand, there's a distinct class of planets called the distant giants or the distant Jovians in the upper right. These planets are more like Jupiter. They're large, usually gaseous. They are far away from their host star, and they're very massive. And again, as you might expect, these are detected almost entirely using the radial velocity technique. And so a reasonable question to ask, especially in light of our own solar system, which has both distant giants in the form of Jupiter and Saturn, and close-in subgiants in the form of Earth, Mercury, Venus, and Mars represented, a reasonable question is, how many systems look like our own solar system in the sense that they have both of these demographics of planets represented? And so the way to answer this would be to pick out the systems that have been characterized using both techniques. Unfortunately, there are very few systems which meet this criterion because surveys involving the transit technique have selected target samples that are essentially disjoint from most of the surveys, most of the samples conducted or used by radial velocity surveys. And so this is where the distant giants survey comes in. So the distant giants survey, I have designed to quantify just one single statistic, the probability of finding a distant giant given already that a system hosts a close-in small planet. So the reasonable place to start in a survey like this is to find a sample of stars that are all known to have transiting planets. So the place that we started was with the TESS mission. TESS stands for Transiting Exoplanet Survey Satellite. It's a multi-year, large-scale, space-based transit detection mission. So there's a telescope up in space that is conducting transit observations, and it's already found a multitude of transiting planets. So we selected a subset of these stars that fit all of our observing criteria, and we are now observing them, following them up to look for distant giant companions. And we also limited our scope to sun-like stars, again, to search for systems that look like ours, like the solar system, broadly speaking. Okay, so for some details on this survey, essentially in a large-scale observational endeavor like this, the name of the game is optimizing telescope usage because telescope time is very expensive. So what we wanted to ask ourselves at the outset was, how can we maximize the number of stars in our survey to get the most statistical power, while at the same time using as little time on the telescope as possible to, again, maximize that number of targets. And so what we found is that because we're searching for long period distant giant planets, we don't have to observe very often. We just have to observe each star about once a month to look for changes in its radial velocity behavior, because these periods of these planets are going to be very long. So we don't have to look for very short period changes in their behavior. Then on top of that, because these planets are so large, they're going to have very large shifts in radial velocity. And so I've given a couple of examples of this. In the optimal case, a very heavy planet, about 300 Earth masses or about 1 Jupiter mass, and at about 2 astronomical units, or about 2 times the separation of Earth from its host star, we get a radial velocity signature of about 21 meters per second. So remember, the peak of that RV curve is out at 21 meters per second. So this is well within our observing capabilities. Even in the worst case scenario, or a worse scenario, at about 100 Earth masses and way far out at 5 astronomical units, we still get a radial velocity signature of about 4.5 meters per second, still above that 1 meter per second stellar noise threshold. So essentially, we don't have to observe these stars to the maximum capability of our telescopes or of our time allotment, because they are larger planets with longer orbital periods. So this allows us to recover a lot of time that otherwise would have been used attaining superfluous precision. And this allows us, again, to increase our sample size and maximize the statistical power of the study. And then as another note, we are observing for about 3 years, although a lot of these planets will be covering or will have orbital periods on the order of 10 years, because we only need to sample a portion of the orbit in order to characterize it. And I'll have more details on that in a few slides. So this is an overview slide depicting the broad kind of bird's eye view status of my survey. On the vertical axis, you can see the 45 or so test targets that have been selected because they are sun-like and have a transiting companion. On the x-axis, you can see the radial velocity time baseline, which basically says when was each radial velocity observation obtained. And so we want to space out these radial velocity observations over a long period. So we don't want to sample too finely, again, because these are long period variations we're looking for. And then as each As we approach a certain amount of time, since each observation has been taken for each star, we want to get another one. So for us, we're looking for about a monthly cadence, about one observation per month per star. And this is what helps me to keep track of that. And in case you were wondering, these gray horizontal bars represent when each star is visible from the Keck telescope in Mauna Kea. So this again helps us to schedule our observations in the most optimal way. So up until this point, I've been talking a lot about the statistical power of the Distant Giant Survey. And it is first and foremost a statistical survey, but that doesn't mean that we can't extract information that's valuable about individual systems. So as each of these systems develops with our radial velocity observations, certain ones of them will start to show promise as subjects for individual characterization. So I've chosen one of my favorites, which is a stellar system that has 3, not just 1, but 3 detected transiting planets by TESS. It also has a distant giant, which made it eligible for inclusion in this survey. And it's even showing evidence for a 5th companion at wider separation. So first of all, you can look at the lower left plot, and the top panel of that plot shows all of the radial velocity observations as a function of time. You can see by eye that there is kind of a large scale sinusoidal motion that is characteristic of this 100-day planet. Once we subtract out that signal from the radial velocity data, we can start to ask ourselves, have we now extracted all of the information from this system that we can? And the answer is no, because we actually see a longer period trend in the residuals. That is the data that has the data that exists once we have subtracted out the known period of this 100-day planet. And that's depicted on the right. You can see that rather than having all of these radial velocity measurements now be flat at around 0, which we would expect if we had subtracted out all of the planet signatures, there's a long period increase in the star's radial velocity, which means that something is actually pulling it away from us over a very long period. And you can imagine zooming out that this curve might actually be part of a very long period sinusoid. And so we went ahead and fit another planet to that. I know it's a little bit small, but what we are detecting right now is another planet on the order of about 1,300 days, an orbital period of about 1,300 days, or around 3 to 4 years. So this is actually a perfect candidate for this survey because the survey is kind of still in its early stages. We are just about completing year 1 of our 3-year baseline. And so by the time the survey completes, we expect to see a much more rounded out radial velocity baseline for this planet, and hopefully for a lot more in our survey. So with that, I'd like to put up my summary slide. So I went a little bit over time, and I will take any questions. Thank you very much. Okay, so one question, do we expect planetary systems to have multiple giants, or is there usually just one at most per system? So this is a great question, and it is something that we will definitely want to address once we have the full results of this current survey. Definitely, it is feasible to have more than one distant giant, as kind of evidenced and is being fleshed out in the system that I just mentioned here. So we kind of hope and we're expecting that there is a second giant here. But as of right now, I think it is not well constrained whether there is usually just one distant giant, although I would expect that there could easily be more. Let's see. Is the ultimate goal to find planets like Earth, and where do we go from there? Awesome question. So because the exoplanet field is so young, there is kind of tons of groundwork really to be laid. So there are all kinds of questions that people are asking. Lots of exoplanetologists study questions that don't really pertain directly to planet habitability. You know, for example, go back here. For example, a lot of people are interested in this exoplanet demographic, these hot Jupiters. These are planets that are really massive, but are very close to their star. So it's kind of twofold reason that they're not habitable, right? So they're large and gaseous, and they're so close to their star that they wouldn't be suitable. But people study those as well. So there are lots of questions pertaining to non-habitability. I personally would, you know, and I think a lot of exoplanet researchers love to find habitable planets and love to address questions of habitability. So that's absolutely one of the overarching goals, though not the sole one. And as for where to go from there, that is definitely a profound question. I think there are already efforts to search for, you know, life or sentient life in the universe, and I think that those questions are going to become more profound, and the ways that we address them are going to become more sophisticated as the research develops and as the field develops. Did I make the Captain Jack graphic? Yes, I did. Yes, I did. I'm still hoping to get a trademark on this and to use it in some future outreach situations. But here, you are the lucky few to enjoy its debut. So yeah, I hope you like it. All right. Well, I think if there are no more questions, then I'll go ahead and stop my share, and I'll turn it back over to Isabel. Thank you.
Thank you, Judah. That was really fantastic talk. Hope you all enjoyed these talks from Judah and Anna and learned a little bit. We are going to finish up here since we're not at a bar. We'll still try to have a little bit of fun. We're going to play some bingo, some astronomy bingo. So we will post in the chat a link here to where you can find your personalized bingo card. If you click the link, the bingo card will come up with some terms that we will be doing sort of as a trivia, and you can click, if you click on the box when a turn comes up, we'll fill it out, and you can just as bingo goes, try to go 5 in a row, up, down, or diagonally. And let me share with you. Okay, so if you get a bingo, or if you get bingo, I'm not sure. Do you say a bingo? Nobody knows. If you get a bingo, you can scream as loud as you want because we can't hear you. Only your household can. Actually, so maybe you shouldn't. Maybe you shouldn't scream because we don't want your household, your roommates or family to not let you join Astronomy on Tap again. But okay, so what you can do is just post in the chat that you have a bingo, and then you can email outreach@astro.ucla.edu after that later, and with just a screenshot of your card and your mailing address, and we can send out a little prize to you. All right. All right, we will go ahead and get started. I'll give about 15 seconds for each question, and I will go through the answers one by one because this is a learning experience. So while it's sort of formed as trivia, you want to find the answer on the first, try to think through the answer, find it on your card, but we'll go through it as well. All right. So our first question is, what is the phenomenon that is used to explain how the universe is expanding at a faster and faster rate? So what is the term for this? Are the slides being shared? Ah, I'm so sorry. It looks like the slides are not being shared somehow. Yay, technology. Okay, since it appears I wasn't sharing the screen previously, I'm just gonna go back to this slide so you can see the email briefly, and then I will go back to this. So our first question is a phenomenon that is used to explain how the universe is expanding at a faster and faster rate.
The sweet love and devotion. Hi, I'm.
Okay, you can see that I am very good at technology, and when playing the Jeopardy music, it went to a commercial, and so I hope that you enjoyed that brief snippet of noise. Anyways, we shall proceed. The phenomenon that is used to explain how the universe is expanding at a faster and faster rate, that would be dark energy. This is different than dark matter. Nobody knows what it is, and you can actually say that because it's true. But it, right, is a term that refers to the stuff that we would attribute to the expansion, the accelerated expansion of the universe. All right, an object whose gravitational attraction is so great that nothing, not even light, can escape. If you haven't gotten it yet, a hint, this was featured in Anna's talk, and as you hopefully guessed, that would be a black hole. So our next term is the violent explosion that happens when a massive star dies. So this one is kind of a fun term. Folks like to say that stars are kind of like pop stars. So the bigger ones, live fast and die young. And that occurs in a supernova, giant explosion. Ripples in space-time caused by colliding black holes. Now this was made popular a few years ago by a detection from, the first detection from LIGO, and so has been in the media in recent years, which is where you may have become familiar with the term. This is gravitational waves. The name of the supermassive black hole in the center of our galaxy. Okay, this is testing our short-term memory. What was Anna talking about? And that would be Sagittarius A star. There are multiple theories actually on why it's named, why the asterisk is there on the A. Some say that it comes from nuclear physics. Others say that, nuclear physics, because it indicates that something is in an excited state. Others indicate that it is named that because it was first identified and seemed as a point source, which is funny because it's a supermassive black hole. Okay, the only thing outside of our galaxy that we can see without a telescope, so with the naked eye, in the northern hemisphere. And as a hint, this is the Milky Way's neighbor galaxy. So this is Andromeda. It's actually pretty cool if you know that you're looking at it, to understand that you're looking at a whole other galaxy in the night sky. But it'll just look like a star, like a regular star in the sky, because it is much further away than the stars that we see. But you can see it on very clear nights if you are not in Los Angeles, but perhaps in the mountains or in the desert. And at certain times you can, if you know where to look, you can see, oh, that star that looks like all the other ones, that's an entire other galaxy. And so from the northern hemisphere, that's the only thing we can see outside of our own galaxy. But from the southern hemisphere, there are a couple of things that are, just as a fun fact, the large and small Magellanic Clouds. All right, I hope you guys are getting close on your bingos. Let's see, what's our next one? Rings of debris orbiting between Mars and Jupiter. So this is the name of what that, like, the ring of debris is called. The asteroid belt, right? So right out in the kind of middle of the solar system, there's just an orbiting set of a bunch of asteroids and debris. Think that Star Wars kind of tries to depict this there, as they're flying through. There's a whole bunch of stuff. Okay, we're getting into some solar system questions. So this next one is a gas giant around which rocks and debris are orbiting, which can be seen from the Earth as rings. Which planet is this? So that is Saturn. Saturn is the one we see that you always see in like the pictures or the little hanging planets from the ceiling. It has the rings around it. So that follows nicely from the asteroid belt question, because it's kind of has to do with these rings of debris and rock. Our next planet in question is, on which planet was the organic molecule phosphine recently claimed to be found? That would be Jupiter, the biggest of the planets in our solar system. So this was an exciting recent paper study that came out. And just a fun fact, not this, but relatedly, Sophia, which is an airborne spacecraft, telescope, has just recently found a tiniest bit of water on the moon. And as I say that, I realize that I completely misled you on the slide. That does not make sense that it would be Jupiter. Yeah, that would be Venus. So I was testing to make sure that you all knew your astronomy. So I hope you didn't listen to me, and I hope you know better. That would be Venus for sure. So moving back to a term that is related to Judah's talk. Someone's got a bingo. We'll finish this term. The planet surrounding other stars outside of our solar system. So what was Judah talking about? So congratulations, Francesca, on your bingo. You can go ahead and email outreach@astro.ucla.edu, and with your email or with your mailing address and your screenshot, and we can send you a little prize. For those of you who want to keep playing, we can do a couple more terms, see if any of you also get a bingo. Bingo, congratulations to Francesca and Nina. Fabulous. So exoplanet, of course, is what Judah was talking about. Now the next question, be similarly related to Judah's talk, the speed at which a star moves towards or away from an observer. And this can be used as a method of detecting planets outside of our solar system. That would be radial velocity. And actually, both Anna and Judah talked a bit about this. This is what both of them mentioned. You can see changes in the spectrum of a star. A theory proposed by Einstein that says that gravity is more complicated than what we can detect on a human scale. And this has been tested by both the orbit of Mercury around the sun and by the orbits of stars in the center of our galaxy. So this is part of what the Nobel Prize winning research recently detected, and we have more bingos with that. Congratulations, Dave and Pratik. Fantastic. So we will go ahead and call it there. Super and Auburn, congratulations. Thank you. Super happy to have you all be playing with us as we launch Astronomy on Tap West LA. And thank you again to our wonderful speakers, Anna and Judo. Judah. I'm so sorry, Judo. Anna and Judah. And we hope you'll join us next time, and perhaps someday in person at a bar in West Los Angeles.